So this theorem due to Gauss, and Gauss himself called this result as this theorem egregium, Latin, so which means that it is a wonderful theorem. So Gauss himself called this as a wonderful theorem. It is indeed a wonderful theorem. It says basically that the Gaussian curvature of a surface, of a two surface, is intrinsic. The key word is that intrinsic. So what does this mean? It just means that the curvature does not depend on how the surface sits in R3, how you view the surface sitting in R3. So in mathematical terms, what it says is that the Gaussian curvature is invariant under local isometries. So what is a local isometry? So diffeomorphism, local diffeomorphism if you want, which preserves the metric. That means it preserves the inner product on the tangent spaces. Okay? So it's not just a smooth map both ways, but it also, that is, it not only preserves the smooth structure of the surface, but it also preserves the inner product structure on each tangent space. See, generally, what is an isomorphism in general? The map which preserves whatever structure that you are looking at. Okay? So if you are looking at groups, group isomorphism, the map which preserves the group structure, right? The group operation. If you have a Banach space, it's a map which preserves the linear structure and also the Banach space structure. That means the norm structure. If you go to Hilbert spaces, an isomorphism would be something which preserves the linear structure and the inner product structure, right? So which in terms of Hilbert space operators would mean that the linear map that you have is a unitary map, unitary operator, right? Linear map which preserve the inner products. Inner product ax comma ay is equal to inner product x comma y. Okay? Isomorphisms, linear isomorphisms, which preserve this inner product structure. These are the unitary maps. So isomorphisms in the category of Hilbert spaces are the unitary maps. So in general, an isomorphism is something which preserves whatever structure that you are looking at. So here, when you look at a surface, you are not just looking at the smooth structure there, but you also are looking at the structure of tangent spaces at each point of the surface. You have curves on the surface. You can talk of lengths of the curves on the surface. So something which preserves all this structure, right, is what it going to be an isomorphism in the category of surfaces, right, on the set of surfaces. So such an isomorphism is called an isometry in this context because it's not only an isomorphism as surfaces, but also preserves lengths and distances. Let us spend some time on this, isometries and local isometries. So what are, if you look at Rn, any Euclidean space, so what are some isometries on Rn? Here we are not looking at the linear structure, right? So only the metric structure. So distance preserving, length preserving, right, and smooth. Translations, right? Translations. Then, what is a translation? For a fixed A, right? TA or something. Translation by A. Any other isometry that you can think of? Rotations, right? How do you describe a rotation? How do you define a rotation? In R2, if you think of a rotation, right? Rotation of right? A point here. So if you write in terms of complex numbers, for example, z is mapped to, say, e power I theta times z. This is a rotation through an angle theta. Okay? So geometrically, of course, what you call as rotation of axis, if you like. Okay. What about, of course, you can talk of rotation about any axis. By the way, what about reflections? Reflections are also isometries, right? But okay, so we'll come to that anyway. So So what is a rotation in R3, for example? So you can look at rotations about any, let's say, about the origin, okay? So rotation about the origin means rotation about any axis, any line through the origin. So for example, the coordinate axis. You can rotate about the x-axis or the y-axis or the z-axis. So how do you, can you write down the map? Even in R2, what is the map? In R2, rotation through an angle theta, r theta, let us say, of xy. So, I mean, you must have, in some place or the other, when you study analytical geometry, you would have studied rotation of axis, the new coordinates in terms of old coordinates, right? X dash equal to something, y dash equal to something. What is that? What are those somethings there? X cos theta, x dash equal to minus y sin theta, x sin theta plus y cos theta, something of this kind, okay? So how do you write it in more compact fashion? Right? What is the matrix that you get here? So it's given by a certain matrix. What kind of matrix is this? Orthogonal. In real case, you say orthogonal rather than unitary. Okay. It's an orthogonal matrix plus it has determinant 1. So it's an orthogonal matrix of determinant 1. Right? So it's what is called a special orthogonal matrix. Two by two special orthogonal matrix. SO stands for special orthogonal. O is just orthogonal. S means determinant 1. Special means determinant 1. That is why we also write SL2R, for example. Special means determinant 1. Conversely, it's an easy exercise for you to show that if you start with any 2 by 2 orthogonal matrix, it is of this form for some theta. Okay, so 2 by 2 special orthogonal matrix means what? So first of all, it is orthogonal. So A transpose is identity, that is orthogonality, and then determinant is 1. So you write out the conditions. So if you take A as ABCD, write out this, that will give, write out A transport, so is equal to identity. So this entry here is equal to this entry in identity, and so on. 4 entries here equal to the corresponding entries in the identity matrix. And then this condition, let's say AD minus BC is 1. So if you try to solve these equations that you get, right, in A, B, and C, D, you will see that you end up with, so A has to be cos theta for some theta, and then D will be sin theta for the same, D also will be equal to A, so on. So you can, so all this involved is, all that is involved is to just solve these equations, okay? This 2 by 2 case, so easy to write down things and solve. So solve the equations to get that SO2 is all matrices of this form. So SO2 is precisely all matrices of this form. It's not going to matter, right? If you, of course, if you restrict to 0 to pi, you are going to get the same set of matrices, okay? But for any theta in R, there is going to be A. This way, you also get a curve in this set of matrices, right? 2 by 2 matrices. Alpha theta equal to this gives you a curve in space of 2 by 2 matrices. This group is isomorphic to the unit circle, cos theta, sin theta, right? The unit circle. Which is all complex numbers z, mod z equal to 1. Just to see that it has a group structure, it's easier if you write it in terms of complex numbers. This is called the circle group, one-dimensional sphere or the one-dimensional torus. That's why I use T for torus. Okay, so in general, so suppose you go to R3, for example, and look at a rotation about one of the coordinate axes, for instance. So how do you write down the map? So points, see, rotation about the z-axis, for example, will do what? Leave points on the z-axis invariant, right? Nothing is going to happen to points on the z-axis. So can you give some map of the type? Suppose you start with the same thing. Add a row and a column. What does this do? So if you we can write down whatever it is, but what does it do with say points on the z-axis? Points on the z-axis means what? X and Y are 0, right? So what are you going to get? So you will get 0, 0, z again. So leaves the z-axis invariant. So this represents a rotation about the z-axis. Similarly, you can write 2 more matrices of this type. So instead of adding this as the last row and the last column, you can add as a first row and first column, or the second row and second column. So correspondingly, you will get rotations about the different coordinate axes. Okay? So these rotations about z axis. Similarly, you can write two more. So again, of course, these are not all, right? You can rotate in R3 about any line through the origin, not necessarily about any coordinate axis. But the point is that any rotation, that is rotation about any line through the origin, can be expressed in terms of rotations about the coordinate axis. Okay, this is the theorem due to Euler, which shows that any rotation in R3 about any line through the origin can be expressed as a product of rotations through the coordinate axis. In fact, Euler showed that any two will do. So rotations through any axis in R3. So by a rotation in R3, what do we mean? Rotation about some line through the origin. Okay, so all possible lines. So all such rotations form a group. The group of all such rotations is the special orthogonal group of order 3. 3 by 3 special orthogonal groups. So this is a group. This is a subgroup, for example, of this, and two other subgroups of the same kind you have. And so let us call it G. So this is, let's say, K3, let's say, okay? Rotations about the third axis, Z axis. So similarly, you have K1 and K2. So K1, K2, K3 subgroups of G. And Euler's theorem, which I mentioned just now, says that any two of these subgroups generate the whole group. Right? Any rotation can be expressed in terms of rotations about two of the axes. You don't need even all the three axes. So Euler's theorem any two of K1, K2, K3 generate the group G. So this is called the group of rotations. Okay. And of course, as we already observed, so this is isomorphic to, as a group, is isomorphic to SO2, right? So each of these are isomorphic to SO2, which in turn is isomorphic to the torus. So these are what are called maximal tori in SO3. Each one of them is a maximal torus in SO3. That means a subgroup isomorphic to a circle or some power of the circle. Of course, in this case, no higher power is possible. So Okay, so you have translations, you have rotations. So incidentally, this is a compact group, closed and bounded. Closed because determinant is 1. Okay? Bounded because the rows are all unit vectors. Any orthogonal matrix, the rows are unit vectors. In fact, a matrix is orthogonal if and only if the rows form an orthonormal basis for the space. It's true for any order. N by n matrix is orthogonal if and only if all the rows or the columns, if you want, form an orthonormal basis for Rn. Okay? So all of them are unit vectors in particular, so it's bounded. So it's a compact. On the other hand, if you look at translations already mentioned, all translations form a group. Composition of two translations is again a translation, right? So group of translations. Any A in Rn gives you a translation by A, right? TA composed with TB is T A plus B. So this group is actually isomorphic to Rn itself. Group of translations of Rn is isomorphic to Rn. A going to TA is an isomorphism. T sub A. And the fact is that any isometry of Rn is a product of translations and rotations. In other words, the group of isometries of Rn. So isometry here only refers to the distance preserving, not necessarily linear. Translations are not linear. Okay? Rotations are linear, but translations are not. So the group of isometries of Rn is usually referred to as the motion group of Rn or the group of rigid motions of Rn. An isometry of Rn is often referred to as a rigid motion. So this is actually generated by translations and rotations. So translations form a subgroup of this, rotations form a subgroup of this. The two subgroups together generate the whole group. Of course, translation is isomorphic to Rn, as I already said. The group of rotations is a special orthogonal group. So as spaces, this also referred to as Mn or whatever, doesn't matter. So this is Rn cross SON, but it is not a direct product of groups, but you have what is called a semi-direct product. So this is but let's not worry about what this means. So, okay. So each. On the other hand, if you look at, say, the sphere, the Euclidean sphere, what are the isometries there in terms of the usual? If you look at a rotation, it's going to fix the sphere. Not the points in individual point, but as a whole, sphere is going to map to itself. So ON acts on the unit sphere. So it's a group action you have. And if you look at points, those orthogonal matrices which fix the last basis element, for example, okay, En. So that is going to form a subgroup which is isomorphic to On minus 1. So as a quotient space, On mod On minus 1 can be identified with this, with the quotient topology here. So you have a group On acting on Sn. So you have a fixed point subgroup. And so the coset space or the quotient space of this will be isomorphic to the sphere itself. So example, what is called a homogeneous space. So in a way, we understand isometries on Rn, or Rn plus 1 for that matter. So we are interested in surfaces, not the ambient space right now. Suppose you have two surfaces, S1 and S2, both n surfaces in Rn plus 1. And if you have a smooth map, from S1 to S2, or have a diffeomorphism, let's say, okay. So F is a diffeomorphism. So it preserves the smooth structure. And secondly, it preserves also the tangent space structure, the metric on the tangent space, which means D, use capital D. So DFP, what is DFP? Is going to be a linear map from the tangent space of S1 at P to the tangent space of S2 at the point, image point f of P. This is an isomorphism, not just an isomorphism, but also preserves inner products, which means what? DFP of V dot DFP of W, or if you want, you can write this inner product way, the Euclidean inner product, so I am writing dot. So this is same as E dot W for all P in S1 and all V and W in where? Here or here? Here, right? Because DFP is acting where? DFP is going to act on the tangent space on S1. So for all V and W in TP of S1. All tangent vectors So in other words, it also preserves the inner products on the tangent space at all points. So this is what is called a local isometry. It's you can work with a patch if you want, but this may not be. So when you say it's a diffeomorphism, you are saying that it's a diffeomorphism onto the image. So if the image is also the whole of S2, that is a local isometry which is surjective, is called an isometry. But as far as say curvature is concerned, for example, curvature at a point, you are going to be concerned only with the local behavior of the function. So what the theorem of Gauss says is that the theorem I wrote down says that local isometries preserve Gaussian curvature. That means if f is a local isometry, the curvature of S1 at the point P is equal to the curvature of S2 at the point f of P, right? So if you want now, you can put something here. Curvature in S1 equal to curvature in S2 at the point f of P. The definition of local isometry involves only the inner product, right? That is the first fundamental form, if you want. The first fundamental form is the inner product in the ambient space. It does not involve the second fundamental form or the Weingarten operator. That means second fundamental form is given by the Weingarten map, right? So it comes from the surface, whereas the inner product comes from the ambient space, right? So if you look at the formula for the curvature that we have written, for example, in the morning, okay, so that involves both the first fundamental form and the second fundamental form. So EFG are the coefficients of the first fundamental form, whereas LM and N, LM and N involve the coefficients of the second fundamental form. Okay? So the curvature a priori depends on both the first and the second fundamental forms. But the theorem of Gauss says it is independent of the second one. It depends only on the first fundamental form. So in other words, it does not depend on the way the surface sits in R3, right? Because it depends only on the inner product in R3 other than the differential structure there. So that is why it is called intrinsic, right? Intrinsic just means invariant under local isometries. So this is remarkable because the construction of the curvature function depended on not just the first fundamental form on the Weingarten map or the second fundamental form, but ultimately Gauss said that it actually independent of any such thing. It depends only on the ambient inner product. That is why it's a wonderful theorem. Okay? So Gauss was justified in calling it a wonderful. Because we are not going to attempt any proof of this theorem or even indicate how the proof goes. The proof actually is has to work with both fundamental forms, and ultimately you throw off anything that comes from this second form. Okay. So it involves the standard proof. I think it goes back to Gauss himself. Involves various quantities, what are called the Christoffel symbols, Gauss's equation, and so on. There are two other things associated with the surface which are also intrinsic, not just the Gaussian curvature, but for example, parallel transport is also intrinsic. Yeah, so parallel transport is intrinsic. Okay, it again depends only on the first fundamental form. So let's say something about Ramanian matrix. So what is a Ramanian metric on a surface? It's a smooth way of assigning inner products to the tangent space at every point. So this we are going to define only in the context of n surfaces in Rn plus 1, the usual setting. Give a name to this. This is the G, usual G, right? This is a classical notation, so we continue to use that, used by Riemann himself. So what does this G do? At each point P, it gives you an inner product on the tangent space at P. So GP is an inner product on TP for each P. So GPV, GPW, right? I don't know. So the inner product, what is the inner product? Right? Symmetric bilinear form. Okay, so GP is a symmetric bilinear form on positive definite bilinear form on TP. So This is the inner product. Okay. So it's the choice of an inner product on each tangent space. So GP is this, but we have to still make sense of. So for every P, you have an inner product on TP. That's what G does, right? But what is this smooth? You have to do it in a smooth way. So everything on the surface we have to do smoothly, right? Whether whether they are functions or vector fields, curves, anything, all of them should be smooth. So what is meant by smoothness there? The choice is smooth. Smooth choice of inner products. So what is the meaning of saying this?